Hi everyone, so today we're going to be having a look at the final section of our course, and it's about nuclear fission and then looking at nuclear fusion. So for fission, there's a few outcomes that we need to look at. There's a couple related to spontaneous and induced nuclear fission, and the rest of them are looking at elements around chain reactions and what's required to keep that chain reaction sustained. Alright, so firstly looking at spontaneous and induced nuclear fission. So nuclear fission, what is it? I guess is the process by which a big nucleus is split into two smaller, lighter, often called daughter nuclei. Now, spontaneous fission can actually occur when some massive nuclei are split into two smaller fragments. Now, spontaneous fission is not a common process, and it doesn't have any industrial relevance. It's not used generally to produce power for nuclear power. Induced fission is more of the one that we're concerned with, and basically that occurs when we have a big nucleus that's being bombarded with neutrons, and it is able to absorb one of those neutrons to form a very excited nucleus, which starts oscillating and vibrating because it becomes unstable, and then as a result of that it splits into two positively charged parts, and often with one or more extra neutron is also released in this reaction. So this is the common process in nuclear reactors for producing power, and it's when a uranium-235 actually absorbs an extra neutron. And you can see from the equation down here that this is the equation for nuclear power production using uranium-235. Alright, so continuing with spontaneous and induced fission. Now, the half-life of uranium-236 is less than 10 to the minus 12 seconds. So we get what's called a secondary decay. That occurs almost immediately. So a secondary decay happens if the new isotope is unstable. So for this reaction that we're looking at here, we've got uranium-235 adding the additional neutron, and it breaks down into two daughter nuclei. We've got a Ba-141 and as Kr-92. So in that process, you also get produced three additional neutrons. So many other isotopes can be produced in this reaction. It's not set which isotope will be formed because there's many different possibilities depending on how that big nucleus actually breaks down. So in addition to the two daughter nuclei, which they've denoted here as Y1 and Y2, they're usually excited, which means the nuclei of those atoms is also oscillating, and then again to return to its ground state, they emit the gamma rays as they decay back to their ground state. Alright, so we get a range of energies and energy levels that can be emitted when a uranium atom is split, but because the reason for this is that the mass of the uranium nucleus, if we add on the additional neutron, is greater or bigger than the mass of the product nuclei and the neutrons that it releases. So the energy that is emitted in this reaction appears as kinetic energy, and it's the energy of the product nuclei as they're moving away from the reaction, plus the energies of the emitted gamma ray photons. So in a chemical reaction, for example, when carbon burns in oxygen to give carbon dioxide, or CO or CO2, then the amount of energy released when the atoms of C and O combine is usually only a few electron volts. However, when we're talking about nuclear reactions, when we have fission, we get millions of electron volts of energy actually being produced. One of the best explanations I've seen of how to explain fission is using the assumption that the nucleus is a water drop, and this is much more easy to visualize. So if we have over in picture number A, we've got a nucleus. All right, it's a uranium-235 nucleus, and you can see there's the inbound little blue neutron. So in picture B, what happens is we've now got an excited nucleus. So it's it's spreading out. It's absorbed that neutron and now it's spreading out. So if we now look at picture C, the Coulombic repulsion of those positive parts is it's vibrating, it's starting to break apart. So you can see that water droplet model coming into its own now. They're separating out, and then when they pull apart like little drops, it undergoes the fission, and that reaction forms two new nuclei, depending on how that actual drop has split, and it also releases some free neutrons, and you can see those there shooting away from the fission site. So in the process of nuclear fission, you often get more than one neutron being emitted in each of the fission processes. So these neutrons can actually can go forth and produce further fissions, and if that happens successfully, then we get the chain reaction that's required to actually start generating nuclear power. So each of the fissions separate a big nucleus into two smaller ones. They result in some neutrons flying out. Those extra neutrons can go on to be absorbed by another nucleus. They can make that nucleus unstable and it breaks, and so on and so forth. So we get this nice chain reaction actually happening. Alright, so now let's have a look in a bit more detail at that chain reaction. So most of the neutrons that are produced in fission have really high energies. They're usually in the order of 1 or 2 mega electron volts. So the probability of that neutron going forth and being absorbed by another uranium-235 nuclei is quite low. They're moving really fast. The idea, they're not going to be captured if they're moving that fast. So in order to slow them down, to be absorbed, they need to be going much slower, and around the order of 10 electron volts or less. And to do this and to slow them down, they use something called a moderator. Now, the most effective moderating materials are those with really low masses and approximately equal to that of the neutrons themselves. So you can think of billiard balls of the same mass colliding. The most effective ones at slowing the billiard balls down are going to be the ones that are about the same size. So here we've got a billiard balls example. We've got A and B going around the same size. You can see that all of the momentum has been transferred to ball B. So before the collision and after the collision, the momentum has been conserved. Whereas in the second example, when we have the mass of A being much smaller than the mass of B, then they're both going to have some momentum, and A still hasn't slowed down as much as we would need for it to be absorbed by another nuclei. Alright, so if we want something that has the same mass of a neutron, then I guess ideally the best moderator would contain hydrogen atoms because they're about equal to a neutron mass. Now the problem with that is that hydrogen also tends to absorb neutrons, and so we need something that's probably a little bit heavier to not be able to absorb the entire neutron. So what they use for that, is heavy hydrogen, which is called deuterium. And they use that in the form of heavy water, deuterium, which doesn't absorb the neutrons and really acts to slow them down enough for it being absorbed. One of the other issues with chain reactions and keeping it going is that the uranium ore that we get out of the ground can't be used to directly give energy in a nuclear reactor. So the fraction of naturally occurring uranium-235 is about 0.8%, and the rest is a different isotope, which is uranium-238. So generally, to put in the reactor, we need uranium-235. So before we're able to use the uranium, it has to go through a process called enrichment, or to be enriched. So you might have heard that term before. Now, the proportion of uranium-235, that useful isotope that they put in the reactor, has to be increased to several percent to be able to get useful power for a reactor. Now, if they're going to be used for nuclear weapons, then that enrichment process needs to continue until uranium-235 is at about 90%. So this process is really difficult, and it's also really expensive. It is possible to produce a reactor operating with natural uranium, but only if the moderator used is heavy water, because it slows the neutrons down enough. But again, that is also really expensive to produce. So many of the neutrons produced in fission are either absorbed by surrounding atoms, or they actually escape through the surface of the reactor. So because of that, reactors need to be massive. Okay. Now, nuclei with atomic numbers between 30 and 60, so in the range of most reactor fission products. They have a mass number up to about 1.5 times their atomic number. So they're really highly radioactive, and they undergo many decay processes. And every time they go through a decay process, they emit beta particles before we find a stable nucleus where they're happy to be. Now, this is why fission fragments and hence really high energy is released into the surroundings when a reactor malfunctions. So it's really important that this is managed really well, because it can be a really dangerous situation. Another important point is that when the fuel rods, the actual uranium-235 in reactors, need replacing, the rods are really difficult to handle, and they're very dangerous and also really hard to get rid of. So there's only a very small proportion of fission isotopes, and generally the cesium ones that are useful in industrial radiography or in imaging and informatic medicine, but most of them aren't wanted. Alright, so summary. About 1% of the neutrons produced in nuclear fission are emitted after a delay of 10 seconds or more. So they're emitted a little bit later. There's no unique fission for any given nucleus. There's many different possible reactions that could result in the production of a huge range of different fission products and isotopes. And the nuclear fission, the nuclei produced by fission reactants, they're likely to have an excess of neutrons, so they're going to be on the high part of our Z versus A graph, so they're going to undergo a series of beta decays, and then they're going to be more radioactive, so they're going to produce beta particles, and they're also going to produce gamma rays, so they're going to be radioactive for a little while until they find their stable isotopes. So let's quickly look at an example of how much energy is actually released during a nuclear reaction. So here we've got a neutron being absorbed by a standard uranium-235 in a nuclear reactor. It's produced 2 daughter nuclei, 3 neutrons, and also a gamma particle. So we've given the masses underneath there. Now we calculate out the mass of the reactants and the mass of the products, and that way, like we've done many times before, we can calculate the mass defect, or the missing mass. And then using our E equals delta mc squared formula, we can work out how much energy that missing mass actually equates to. So we can see in this equation here, for the nuclear fission of one atom, it produces 205 mega electron volts of energy. Right, so that's a huge amount of energy. So generally what we try and do is harness that for nuclear power. So our application for nuclear fission is the production of nuclear power, and we have to be able to answer the following outcomes here. So nuclear fission power plants are not dissimilar to our coal or fossil fuel power plants. They have a source that produces steam or hot water. The steam is then used to turn a turbine, and the turbine produces the electricity, which is collected and used for powering of homes. Now, for a nuclear reactor, the only difference is that instead of burning coal to produce the heat, they use a nuclear reaction. Now, over on the first part here, we can see that we have the actual core of the nuclear reactor. So here, that's where the fuel and the moderator goes. So the fuel rods, usually uranium-235, and the moderator, which slows down the absorption of the neutrons. We also have something called control rods in there, which will be able to absorb any additional neutrons to keep the reaction at the right level. And then it goes through heating the steam, heating the water, creating the steam, turning the steam turbine, and then creating the electricity, much the same way as a regular power plant. So the core of the power plant actually consists of the fuel rods. So they're the ones that are made out of the enriched uranium, so uranium-235, and the moderator. So remember, the moderator is what slows down the neutrons so that they're able to be more readily absorbed by the next uranium molecule to continue the chain reaction. Now, in this case, the moderator is water, which becomes very, very hot, and the fuel rods are stationary, but there's also something called a control rod, which can get lowered into and out of the actual core, that can control the rate at which the nuclear energy is produced, and also the rate of the reaction that's continuing. So these control rods, or sometimes they're called safety rods, are actually made out of cadmium or boron, and both are elements which actually absorb really strongly absorb neutrons. So the control rods are moved in, down into the core to actually slow down the rate of reactions, because they will absorb all of the free neutrons, and if the free neutrons are absorbed, there's no neutrons to go on and continue the chain reaction. So the aim is to keep the reaction just critical, so that the nuclear reactions are maintained at a steady rate by the released neutrons from each of the fission reactions. So this process of having control rods to be able to really specifically control the rate of reaction would not be possible if some of the neutrons were not delayed when they're emitted. So sometimes when the fission happens, the neutrons are released up to 10 seconds later. So this gives the control rods enough time to be able to react to the situation as needed. So at this point, energy is transferred from the reaction in the form of heat energy that's carried off either by water or sometimes by liquid sodium, and then the rest of the power plant is similar to that of a normal coal or fossil fuel power generator. So nuclear reactors, after they've been built, can be used to produce electrical power relatively cheaply. They have the advantage that no greenhouse gases are actually produced continuously throughout the energy production, whereas an oil, natural gas or coal plant is going to be releasing carbon emissions the entire time. So in addition, we're not likely to run out of the basic fuel, which is the uranium-235/238, as the supply is not as limited as the supply of like fossil fuels. However, there is a danger and a downside to nuclear power, and most people are very tentative with the choice of getting on board with nuclear power. So they can be very, very dangerous. Although they have the extra shutdown controls and control rods that happen in case of emergency, it's still sometimes a very touchy subject for some people about whether or not they approve of nuclear power. So there is also the fact that they do produce thermal pollution or heat pollution into the environment, and also normal power stations do this as well. It's just a byproduct of the actual energy production. So in addition to the materials used, they're not very nice to handle. So liquid sodium, heavy water, all of these things, beryllium, and all the isotopes that are produced are also very highly radioactive. So they're not nice materials that are contained within a nuclear reactor. So the other problem is that the ionizing radiation that's produced by the nuclear fissions also breaks down and destroys the structure of the building materials. So the steel and the concrete that are used to actually make the nuclear power plant actually gets weakened and is broken down over time. So as a general rule, nuclear power plants only have a lifetime of about 30 years. So after that, you're left with a big lump of very radioactive material that can be very difficult to dispose of. So there are a few safety concerns with regard to nuclear power plants, and the handling and safety and storing of old fuel rods is a huge problem. So reprocessing the actual fuel rods into something more purposeful is quite dangerous, and also the storage of the spent rods is a huge problem. Nobody really wants to have these spent fuel rods, and so nuclear waste facilities are actually quite a popular choice for making money, and hence why South Australia was investigating whether or not we should get a nuclear waste disposal facility, because of the lucrative nature of setting one up, because nobody wants to actually store their nuclear power, the actual rubbish from the nuclear power plant. Reactor accidents is also a huge issue, and people are quite fearful of. They've happened numerous times around the world, and they're often said to be due to technical problems, but generally it comes back to human error, which if you are having humans work at the plant, can never be totally eliminated. And also, still many countries around the world completely rely on nuclear power, and if it was banned, they would have to be very, very careful about what they did in terms of their energy production. All right, so just a quick summary of the disadvantages of nuclear reactors. Safety during transport of the nuclear materials, safety during the enrichment process of actually getting the percentage of uranium-235 up to a high enough usable percentage. There's the disposal dramas, I guess, around the nuclear waste disposal. There's the possible leakage of radioactive material. There is the risk of accidents actually happening when the reactor is operating, making sure that there's safe operating conditions for all of the workers, and also the surrounding community and making sure that they're all safe is a really expensive part of setting up the initial setting up of the reactor. And also because of the emitted radiation and the weakening of the structure of the power plant, then any reactor has a limited lifetime. So then all of the parts of the core will show significant radioactivity because it will have absorbed all of the radiation. It means that there's going to be a problem in disposing of that material, as well as the spent fuel rods and the normal material that you need to dispose of. But lastly, there are a few advantages to utilising nuclear power, and that is that it's a known technology. It's relatively abundant uranium fuel resources, especially when we're talking here in Australia. It doesn't produce as much greenhouse gas emissions as a coal-producing power station, and cost-wise, it's fairly competitive with its conventional power plants. It also can be used by countries that don't have significant coal deposits. So overall, as with anything, there are the pros and the cons for the application of nuclear power.